Welcome back to the Deep Dive. This is where we take those big, complex topics, dive straight into the source material, and, well, basically give you everything you need to get up to speed fast.
That's the idea. You bring the curiosity, we sort through the data.
And today, we are definitely diving deep. We're heading back to the Apollo era, specifically to Apollo 16.
Right, Apollo 16, the penultimate lunar landing, April 1972. And this one, well, it was a mission packed with ambition, some serious technical drama, and ultimately a pretty major scientific surprise.
Okay, so scientific surprise and technical drama sounds like we've got a story here. We've got the usual wealth of NASA sources, right? Voice transcripts, mission reports, scientific analyses, the statistical stuff.
Oh, absolutely, the full spectrum. And they all paint this picture of a mission really designed to push the scientific envelope, especially lunar geology. Our job today really is to sift through all that and pull out the core story for you.
So the mission's main goal,
Yeah.
it wasn't just another landing, was it? It was about where they were going.
Exactly. The whole point was exploring somewhere completely new. Apollo 11, 12, 14, 15, they'd all landed on the Mare, those dark, relatively flat plains, basalt flows mostly.
Familiar territory, geologically speaking, by that point.
Kind of, yes. But Apollo 16 was aiming for the Descartes Highlands, a completely different environment, bright, rugged, ancient terrain.
And the Highlands weren't just picked randomly, were they? There was a specific scientific reason.
Oh, very specific. The prevailing theory at the time was that the highlands might be formed from ancient, thick, viscous volcanic flows, something different from the Mare basalts. Scientists thought this area held the key to the moon's very early history, maybe even its original crust.
High-stakes science, then, in a place that looked, well, pretty challenging to land on, let alone explore.
Extremely challenging, high risk, high reward, and NASA put together quite a unique crew to handle it.
Let's talk about him. The commander was John Young.
John W. Young, an absolute veteran. This is already his fourth space flight. He'd flown Gemini, Apollo 10 to the moon. Incredibly experienced, famously cool under pressure, just unflappable.
Yeah, okay. The steady hand at the helm.
Definitely. Then the lunar module pilot, the one who'd walk on the moon with Young, was Charles M. Duke Jr.
Charlie Duke. He was the rookie on this flight, right? But not exactly unknown.
Not known at all. He was actually the voice of Capcom during the Apollo 11 landing. The famous, "Roger, Tranquility, we copy you on the ground, you got a bunch of guys about to turn blue, we're breathing again, thanks a lot."
That was Charlie Duke. Wow. So he goes from mission control for the first landing to walking on the moon himself.
Exactly. Highly trained, especially in geology for this mission, and he actually became the youngest person to walk on the moon.
Quite a step up. And completing the crew.
Ken Mattingly. Thomas Kenneth Mattingly II. He was the command module pilot.
Ah, Mattingly. His story's interesting too, isn't it? He didn't fly on his originally scheduled mission.
That's right. He was famously pulled from the prime crew of Apollo 13 just days before launch because he'd been exposed to German measles, which he didn't even end up catching. Huge disappointment for him, obviously.
So Apollo 16 was his comeback, his chance to finally fly to the moon.
It absolutely was. He orbited the moon in the Command and Service Module, the CSM, which they called Casper. While Young and Duke were down on the surface in the lunar module Orion, Mattingly was handling the complex orbital operations, running experiments from above, and basically holding the whole mission together from orbit, a really critical role.
So, a veteran commander, a rookie moonwalker with a famous voice, and a pilot making his comeback flight. Quite the combination for a mission aimed at the unknown.
A unique crew for a unique destination.
Okay, let's place Apollo 16 in the bigger picture.
Yeah.
We have sources like Apollo by the numbers that let us see the stats, the context. Where did this mission fit?
Well, numerically, it was the 11th crewed Apollo flight overall. But more importantly, it was the fifth successful landing. It came after Apollo 15, which had been a huge success, the first of the big scientific expeditions.
Up to the J mission, right?
Exactly. And Apollo 16 was the second J mission. It really built on what 15 had achieved and paved the way directly for Apollo 17, the final landing. So it's right there near the climax of the whole program.
And by this point, 1972, the goals had really shifted from, say, Apollo 11.
Yeah.
It wasn't just about getting there and back anymore.
Not at all. If you look at the official mission objectives, the focus is overwhelmingly on science. The mandate was clear: conduct a program of scientific exploration of the moon, and just as importantly, continue developing the human capability to work effectively in the lunar environment for extended periods.
It sounds like they were really trying to turn the moon into an operational field site for geology.
That's a great way to put it. It wasn't just planting flags and grabbing a few rocks anymore. It was about systematic traverses, careful documentation, deploying complex experiments,
Yeah.
maximizing the scientific return on this incredible investment.
And that needed better tools, better hardware. You mentioned the J-series missions. What did that actually mean for the astronauts in the spacecraft?
It meant significant upgrades. The J-series missions were designed for longer stays on the moon, up to 3 days on the surface, compared to maybe 30 hours or so on earlier missions.
Wow, 3 days.
Yeah. So the CSM and, crucially, the lunar module had beefed up life support, more oxygen, water, power. The LM also had an improved engine and landing gear for potentially rougher sites. And, of course, the big one,
The lunar rover.
the Lunar Roving Vehicle, the LRV. Apollo 16 carried the second one to the moon. This wasn't just a nice-to-have, it was fundamental to the J missions.
How did it change things so drastically?
It completely changed the scale of exploration. Before the rover, astronauts were limited to how far they could walk safely from the LM, maybe a few kilometers max. You know, Apollo 14 had that little handcart, the MET-T, but it wasn't powered.
Right, the rickshaw.
Yeah. The LRV was a game changer. It was an electric car, basically. It allowed Young and Duke to travel much further, much faster across difficult terrain. They could conduct these extensive geological traverses, stopping at multiple points of interest miles away from the LM Orion.
So it turned them from localized explorers into regional geologists.
Precisely. On Apollo 16, they ended up driving about 26.7 kilometers, almost 17 miles, over 3 EVAs. That kind of range was unthinkable just one mission earlier, before Apollo 15 debuted the rover. It let them access features like Stone Mountain and Smoky Mountain, sample different geological units, things they simply couldn't have reached on foot.
And carry more stuff, presumably. Tools, samples.
Absolutely. The rover acted as a mobile workbench and a transport vehicle. They could load it up with geological tools, cameras, sample bags, and importantly, bring back a lot more rock and soil samples, over 95 kilograms on Apollo 16.
Wow. So the rover wasn't just transport. It was an integral part of the scientific strategy, enabling them to tackle a site like Descartes.
Couldn't have done Descartes without it. The terrain was too rough, the points of interest too spread out. The LRV made the J-series science possible.
Okay, let's zoom in on that landing site. The Descartes Highlands. Why there, specifically? What was the big scientific question they were trying to answer?
As we touched on, the big idea was volcanism. Looking at the Descartes region from orbit and through telescopes, it had features that looked like potential volcanic domes and flows. And crucially, it was in the highlands, this bright, rugged terrain that makes up most of the moon's surface, but was thought to be geochemically different from the dark mare plains.
So they thought it might represent a different kind of lunar volcanism. Older, maybe, or just chemically distinct.
Exactly. The hypothesis was that these highland features might be made of thicker, more silica-rich lavas than the runny mare basalts. Some scientists expected to find materials rich in creep, that's potassium, rare earth elements, and phosphorus, which is often associated with later stages of volcanic activity or specific geological processes. They were hunting for clues about the moon's internal differentiation and thermal history.
So Young and Duke weren't just astronauts. They had to be trained field geologists to even attempt that.
Intensely trained. They spent hundreds of hours training with geologists, learning to identify rock types, understand geological formations, describe landscapes accurately, and collect samples strategically. They did field trips to volcanic areas, impact craters, places on Earth that mimicked lunar terrain.
Because they were the scientists' eyes and hands on the moon.
Precisely. The science team was back in Houston, listening in, looking at fuzzy TV images. Young and Duke had to be able to make real-time geological observations and decisions. They had a packed schedule of EVAs, specific sampling locations planned, but they also needed the flexibility to investigate something interesting they spotted along the way.
And they had the tools for the job, right?
Yeah.
Not just hammers and scoops.
Right. They had specialized rakes for collecting smaller fragments, core tubes for sampling below the surface, drills for getting core samples out of boulders, cameras for documentation, a whole suite of geological tools, all carefully designed for use in bulky spacesuits. The sample catalogs from the mission detail every single item they collected and the tool used.
But the site itself posed challenges even before they landed, didn't it? You mentioned the brightness.
Yes, the albedo. The highlands are much brighter, more reflective than the dark mare sites. This high albedo could cause intense glare during the final descent phase, making it harder for Commander Young to read the terrain, judge slopes, see shadows that indicate boulders or craters.
Like trying to land on snow on a sunny day.
Sort of, yeah. Plus, the highlands were just generally rougher terrain, steeper slopes, more boulders, potentially deeper, looser regolith, the lunar soil. It demanded pinpoint piloting from Young and put the lunar module Orion's landing systems to the test.
So everything about this mission, the location, the crew's training, the rover enough, it was all geared towards tackling this specific, challenging, scientific question about lunar origins.
It really was. Exploration at its most focused, trying to verify a major hypothesis.
But before they could even get to the geology, there was some serious drama in lunar orbit, wasn't there? Something that nearly scrubbed the landing entirely.
Oh, absolutely. This is a key part of the Apollo 16 story, often overlooked. After they'd successfully entered lunar orbit, settled in, and Young and Duke were preparing to undock the LM Orion for descent, Ken Mattingly detected a problem back in the command module Casper.
A problem with the main engine, the big one they needed to get home.
Exactly. The Service Propulsion System, the SPS engine. Mattingly was running through some checks, and he noticed that the backup control system for the engine's gimbaling, its ability to steer, was oscillating, sort of wobbling, when it shouldn't have been.
That sounds not good, especially for the engine you're relying on to blast you out of lunar orbit later.
It was extremely serious. Any potential issue with the main engine was a potential showstopper. If that engine failed later, they'd be stranded. Mission rules were very strict about engine safety.
So what happened? Did they have to call off the landing?
It came incredibly close. Mission Control in Houston immediately put a hold on the undocking and landing sequence. Young and Duke were suited up in Orion, ready to go, and they were told to wait.
How long did the delay last?
It was a tense 6 hours. 6 hours where the landing hung in the balance. Engineers on the ground were scrambling, running simulations, analyzing the telemetry data, pouring back from Casper. They needed to understand why the backup system was oscillating and, crucially, whether it posed any risk to the primary system or the engine's ability to fire correctly later for the burn home.
What was the mood like? For the crew in orbit and the controllers on the ground?
You can hear it in the voice transcripts, actually. Very calm, very professional, but you can sense the underlying tension. Young and Duke were basically told to power down systems in the LM and get some rest, but you can imagine how difficult that must have been. Mattingly was working closely with Houston, running diagnostic tests. On the ground, it was all hands on deck in the control center and the back rooms.
So how did they resolve it? What was the final call?
After hours of intense analysis, the engineers determined that the oscillation in the backup system, while not ideal, wouldn't affect the primary gimbal control system. They figured out a workaround procedure for Mattingly to use that would prevent the oscillation from causing any real problems during the critical trans-Earth injection burn later.
So they decided it was safe to proceed.
Yes. It was a calculated risk, but based on the analysis, Flight Director Pete Frank made the call with the backing of the engineering teams. They gave the final go for undocking and landing. But it was a stark reminder of how complex these machines were and how close they were operating to the edge. It really showcased the maturity of the program, though the ability to diagnose and work through a major in-flight anomaly under extreme pressure.
Incredible. So after a 6-hour cliffhanger, Orion finally got the green light to head down to Descartes.
Right. The drama wasn't over, but the immediate crisis was averted, and the scientific mission could finally begin on the surface.
All right, so Orion lands safely in the Descartes Highlands. Young and Duke step out. What did they find? Was it the volcanic wonderland they expected?
Well, the landing itself was spot on. Young handled the bright, rough terrain perfectly. But almost as soon as they got out and started looking around during that first EVA, things didn't look quite right. The rocks just didn't seem volcanic.
How could they tell?
They were looking for specific textures, minerals, structures associated with lava flows or volcanic ash. Instead, what they were seeing were rocks that looked broken, fragmented, jumbled together. John Young in particular kept commenting that it looked more like ejecta, debris thrown out from impact craters rather than flows.
So even on the first day, the expected picture wasn't matching reality.
Not really, and this continued throughout the 3 EVAs as they drove the rover further out to places like Stone Mountain and Smoky Mountain, sampling different areas identified from orbit as potentially volcanic.
Let's talk about that driving. John Young apparently got quite enthusiastic with the rover.
Oh, he did. He really put the LRV through its paces. There are famous clips of him skidding the rover, bouncing over craters. He apparently called it the Lunar Rover Grand Prix and even set an unofficial lunar speed record, though NASA wasn't exactly encouraging that. But it showed the rover's capability on rough ground.
Okay, so while Young is having fun driving, they're collecting samples. What kind of rocks were they finding, if not volcanic?
They were finding breccias. Lots and lots of breccias.
Okay, you mentioned breccias earlier. Remind us what they are.
A breccia is basically a rock composed of broken fragments of other rocks or minerals all cemented together. Think of it like concrete, but made naturally. The fragments can be sharp and angular.
And the Apollo 16 breccias, what do they indicate?
They were overwhelmingly impact breccias, rocks formed by the intense heat and pressure generated when meteorites smash into the lunar surface. The impacts shatter the existing rock, throw it out, and then the heat and pressure weld these fragments back together into new rocks. Some were also impact melts, where the rock was completely melted by an impact and then solidified.
So instead of rocks formed by heat from inside the moon, they were finding rocks formed by heat from outside impacts.
Exactly. This was the huge scientific surprise of Apollo 16. The Descartes Highlands weren't shaped by ancient lunar volcanoes. They were shaped by billions of years of relentless meteorite bombardment. The entire landscape was essentially a massive debris field from countless impacts, big and small.
That completely overturns the original hypothesis, doesn't it?
Completely. It fundamentally changed our understanding of how the lunar highlands, which make up most of the moon's surface, were formed. It showed that impacts, not volcanism, were the dominant geological process shaping that ancient terrain.
Did they find any volcanic rocks?
Very, very few, and none that matched the type they were looking for. The evidence was just overwhelmingly pointing towards an impact origin for almost everything they sampled.
And they brought back some significant samples, right?
Yeah.
Any famous ones?
OS. The most famous is probably sample 61016, nicknamed Big Muley. It's a large breccia weighing nearly 11.7 kilograms, or about 26 pounds. It remains the largest single rock brought back from the moon by any Apollo mission.
Wow. So the mission was sent to find volcanic evidence, found almost none, but instead delivered proof that the highlands were built by impacts. A successful mission, but not in the way anyone expected.
Precisely. It's a classic example of scientific exploration. You go looking for one thing, but the real discovery is often the unexpected thing you find instead. And it relied heavily on Young and Duke acting as true field geologists, recognizing that what they were seeing didn't fit the pre-mission models.
Beyond the big science and the technical drama, there were some very human moments on Apollo 16 too, weren't there?
Absolutely. These missions were flown by people after all. One of the most touching stories is about Charlie Duke.
The family photo.
That's the one. Before the mission, he had a portrait taken with his wife, Dorothy, and their two young sons, Charles and Thomas. He had it encased in plastic, and during one of the EVAs, he placed it on the lunar surface and took a picture of it sitting there on the gray dust.
Why did he do that?
He said later it was just to show his kids, that Dad had really been there, to leave a little personal touch. On the back, he'd written, "This is the family of astronaut Duke from planet Earth, landed on the moon, April 1972. It's just a lovely, simple human gesture amidst all the high technology in geology.
That photo is still up there, presumably.
As far as we know, yes. Though the intense UV radiation and temperature swings have likely completely faded the image by now, but the act itself is what's remembered.
A little piece of family history left on another world. What about Ken Mattingly, up in orbit? He wasn't just flying Casper, was he? He had work to do, too.
Oh, absolutely critical work. While Young and Duke were exploring Descartes, Mattingly was operating a whole suite of scientific instruments housed in the service module's SIMBay, the Scientific Instrument Module Bay.
What kind of instruments?
He had high-resolution mapping cameras, a panoramic camera, a laser altimeter to precisely measure the lunar terrain height, and various spectrometers, gamma-ray, X-ray, alpha particle, to map the chemical composition of the surface below.
So he was creating a detailed map of the areas he flew over.
Exactly. His work provided crucial context for the samples Young and Duke collected, and also mapped large areas of the moon that weren't visited on foot. His orbital science was a major component of the mission's overall scientific return.
And he also had an EVA to perform, didn't he? Not on the moon, but...
Right, a deep space EVA. On the coast back home, after leaving lunar orbit, Mattingly had to go outside the command module into the vacuum of space to retrieve film cassettes from those cameras in the SIMBay.
Wow. Floating in space between the Earth and the moon.
Pretty much. Charlie Duke stood in the open hatch to assist him, but Mattingly maneuvered himself using handrails back along the service module to the sim bay, retrieved the film, and brought it back inside. It sounds routine now, perhaps, but it was only the second time such a deep space EVA had been done. It was essential for getting that precious orbital imagery back to Earth.
So from family photos on the surface to spacewalks halfway home, Apollo 16 had its share of memorable human moments alongside the science and engineering.
Definitely. It underscored that these complex technical operations were ultimately human endeavors.
So pulling it all together, what's the lasting legacy of Apollo 16? How should we remember it?
Well, I think there are two main pillars to its legacy. The first is obviously the scientific discovery. Apollo 16 fundamentally rewrote our understanding of the moon's crust, especially the highlands.
The shift from volcanism to impact bombardment as the primary shaping force.
Exactly. Proving that the bright, rugged parts of the moon were essentially ancient surfaces pulverized and rebuilt by meteorite impacts over billions of years. That was a huge contribution to planetary science, affecting theories about the early solar system and the formation of other rocky bodies, too. It was discovery through surprise.
And the second pillar.
The second is operational. Apollo 16 really demonstrated the maturity and resilience of the Apollo system, especially the J-series hardware. They successfully operated in a very challenging, previously unknown environment. They made extensive use of the rover for large-scale geology, and crucially,
They handled that major engine anomaly.
right, they detected, diagnosed, and safely worked around a potentially mission-ending problem while in lunar orbit. That showed incredible skill and cool-headedness from both the crew and ground control. It proved the system and the procedures could handle unexpected crises far from Earth. That built enormous confidence.
So it cemented the value of the rover, proved the hardware in tough conditions, and showed they could manage serious problems in deep space.
Yes. It confirmed that the Apollo program had reached a peak of operational capability. They could reliably send humans to complex lunar sites, conduct sophisticated science for days, and manage significant in-flight issues.
And that directly set the stage for the final mission, didn't it, Apollo 17?
Absolutely. The success of Apollo 16, both scientifically and operationally, despite the surprises and the engine scare, gave NASA the green light to proceed with the even more ambitious Apollo 17 landing at Taurus-Littrow, which included sending a trained geologist, Harrison Schmitt, to the moon. Apollo 16 was the vital final proving ground.
Okay, so to wrap up our deep dive on Apollo 16, a mission aimed squarely at the challenging Descartes Highlands with rigorous scientific goals.
Goals that were centered on finding evidence of ancient volcanism driven by a crew combining veteran experience, rookie enthusiasm, and a comeback story.
Commanded by John Young, with lunar module pilot Charlie Duke walking the moon and Ken Mattingly expertly piloting the command module Casper in orbit.
But the mission delivered a major surprise, finding impact breccias, not volcanic rocks, forcing a fundamental rethink of how the lunar highlands formed.
And it overcame a serious technical challenge with the main engine just hours before the landing was scheduled, showcasing the incredible skill of both the crew and mission control.
And thankfully for us, the sheer depth and complexity of this mission, the science, the operations, the human moments, it's all preserved in incredible detail in those NASA historical records we talked about. The Apollo Lunar Surface Journal, the Apollo Flight Journal, Apollo by the Numbers, the science reports.
Which means the story isn't necessarily finished, right?
Not at all. Which brings us to a final thought for you. Think about the sheer volume of data generated by just this one mission. Hours of voice recordings, thousands of photographs, detailed telemetry streams, technical debriefings, sample analysis that continues even today.
It's almost overwhelming to contemplate.
It is. And it makes you wonder, with all that data collected nearly half a century ago, now accessible through archives and databases, what connections haven't been made yet? What subtle pattern in the seismic data, or overlooked feature in an orbital photo, or maybe even an offhand comment in the transcripts, might still be hiding, waiting for perhaps new analysis techniques, AI, or just a researcher with a fresh perspective to uncover something completely unexpected about Apollo 16 or the moon itself.
The potential for discovery might still be buried in the data. A fascinating thought. Knowledge is out there.
Waiting to be synthesized.
All right, before we go, let's run through Apollo 16.
By the numbers.
Okay, total number of crewed Apollo missions flown, 11.
Total successful lunar landing missions, with Apollo 16 being the fifth.
6. Year Apollo 16 flew, 1972.
Landing site, chosen for its unique highland geology. the Descartes Highlands.
Total distance driven in the lunar roving vehicle across 3 EVAs, 26.7 kilometers or about 16.6 miles.
And the unofficial lunar speed record set by John Young during that driving, about 18 kilometers per hour or 11.2 miles per hour. Ha! Yes, the Lunar Grand Prix element.
Total time spent by Young and Duke outside the LM on EVAs, 20 hours and 14 minutes.
Total mass of precious lunar samples returned to Earth, mostly breccias, 95.8 kilograms, or about 211 pounds. That includes Big Mooley.
And the number of astronauts who walked on the moon during Apollo 16, 2, John Young and Charlie Duke.
An incredibly productive and revealing mission, despite, or maybe even because of, the unexpected turns.
Absolutely. That wraps up this deep dive. Join us next time.